Hello everyone, welcome back. So, in this few lectures, we're going to be going over Cartesian vectors and how we add and subtract them. You're like, wait a second. Didn't we do vectors? We did that already. You're right. However, we did vectors with force. I want to make sure that you know how to do it with things that aren't forces. And we're going to learn some other ways of working with these vectors. Okay, now if you're here, hopefully you've already taken the reading quiz because you can't see the PowerPoint without it. So go ahead and do that reading quiz. It is required. And now let's jump right in. Okay, so applications. So why do you need to know all this stuff? Well, for example, we have many structures that involve three-dimensional space. You're like, wait a second. 3 dimensions? Yes, 3 dimensions. You have to do work in 3 dimensions. I know I'm a terrible teacher, but in the end, it adds like 2 equations later on and 1 equation right now. So it's not all that hard. In many cases, it makes things easier. Not all, but many. Okay, so in this case, we have a power pole, and it has guy wires to keep it upright even in strong winds. Now, how would you represent the forces in the cables using Cartesian vector form? Okay, like, well, Cartesian vector, what does that mean? Let's talk about the x, y, and z components. We've already done that with forces before using triangles, and so it's the same thing here. Like, what about that z component? Just look at it in the xy plane, solve for that, and you can look at it in the YZ or XZ plane. We'll get there. You'll know how to do it. Don't worry. We'll do some examples together. Everything will make sense. Okay. Now, what about a radio tower? Same thing. We have these forces. We know where the ends of the tower are. How do you figure out the resultant force that's acting at the top of the tower? Well, we're going to have to break all those forces into components, and then we're going to have to add them all together to see what the force at the top of the tower is actually going to be. Now, you look at this, it looks pretty terrible. There's a whole lot of distances right here, like 16 meters, 18 meters, 24 meters. This is just, it doesn't look fun. It doesn't look fun. And so from that, we have to break everything into components. And you might be like thinking, oh my goodness, this sounds terrible. And in some ways it can be. However, there are ways where we can make things a bit simpler on ourselves, as we'll learn in a little bit. So don't worry too much. There's lots of angles here. There's a little bit of trig, but we have some good shortcuts we're going to learn about eventually. But first, let's get into what a Cartesian vector actually is. So a Cartesian unit vector. So for a vector A, with a magnitude of A, and a unit vector is defined as this. So we take our vector and we divide it by its magnitude. Now, what does this do? Well, it makes its magnitude 1. So it's just the direction. It's going that way. I can't see my finger. That way. There we go. It's going up. It's going sideways. It's going diagonal. Whatever it is. It's pointing that direction, but it has no magnitude. It means it's just 1. It doesn't go anywhere. It's also dimensionless. It has no units. This is a good thing because you might have a position vector from one point to another. You're like, well, how much, let's say you have a position vector for some rope, okay? So you know where both ends of the rope are? You can get a position vector for that. Well, if there's a force going down that rope, well, guess what? That force is going down the same vector as that position vector, or in the same direction at least. So we can use its unit vector to help us. And it always points in the same direction as our original vector A. Now, the unit vectors in the Cartesian coordinate system are I, J, and K. You're like, wait a second, so that's why I, J, and K. Yes, that's why I, J, and K. And here they are. I with the X, J with the Y, and K with Z. That's how they're defined, so make sure you do it accordingly. Now, if you're trying to figure out, well, which direction is X, Y, and Z positive supposed to go, use the right-hand rule. You can see this right hand right here. That is what's trying to show you. So just take your hand, take your right hand, not your left hand. Your thumb is the z-axis. Your wrist is the y-axis. And your fingers, when you put them out straight, they're the x-axis. It's hard to show here, but it works, okay? Right hand rule. You are wrapping your fingers around the z-axis and pointing straight up it. Don't forget that. Okay, so with that, hopefully that helps you. Just look at this video to help, or look at this little image right here to check yourself. That is what a Cartesian unit vector actually is, and that's how we define their directions. So how do we represent a vector in Cartesian vector representation? You probably already know this because we've done example problems and you saw it. You saw it a couple times, actually 3 times in the previous set of lectures. So it's going to be here. There we go. So if we have a vector, let's just call it A, with a magnitude A going in some direction. Well, if we break it up into its components, the x component goes in the I direction. The y component goes in the j direction, and the z component goes in the k direction. So the I, j, and k unit vectors give the direction. The ax, ay, and az magnitudes, or the scalars, give the magnitude of each of those directions, or each of those components. So this is how you constantly see it. If you're adding together 2 vectors, you're going to add the components, so be careful about that. But we'll do that a little bit later. We'll do that today. Okay. Now, then here's an interesting and very important detail. What about the projection? Projection is more like a shadow. Imagine that you have a lamp way up here, and it is just shining a big bright beam of light onto the surface. And imagine that that arrow is blocking the light. Well, what you would see on that surface is a shadow right here. And that is usually called A prime. It is the projection, or in my case I'm going to say shadow, of the vector A on the xy plane. So it's what that component is in here. As you can see, if I'm making a right triangle of it, this is this component right here, the bottom component. And I still have that z component. So we can find that using the same approach as a 2D vector, because both of these vectors, this guy right here, this guy right here, and I'm getting way too many lines here, erasing everything. This vector and these 2 components are all in the same plane. And so it's just like our 2D case. We could find A prime by looking at this together. So it's just going to be ax plus ay squared, so ax squared plus ay squared, and then the square root of that. And then we can find the magnitude of A, or our z component, whatever we want, by using the Pythagorean theorem with the A prime vector, this new vector that we have created. And so we can then solve for this. And we can just prove that all this is correct because we can bring back a sort of form of Pythagorean theorem for 3-dimensional space and see that it's all equal to each other. So A would be equal to A prime squared plus AZ squared, check. But A prime squared is simply equal to AX squared plus AY squared square root. So we plug that in here and we get that A is equal to AX squared plus AY squared plus AZ squared, all that under a square root. Okay, so with that, let's stop here. You've seen the Cartesian vector representation. You've seen the A prime, this whole A prime thing, it comes up a lot. Make sure that you realize that you can do that and how you would take certain components to figure out the projection. It makes things really easy, or much easier. Okay, but with that, let's stop here, and I'll see all of you next time. Bye-bye.